What's up, scholars? This is a quick set of notes here all about the topic impulse here in our unit on momentum and impulse. Sometimes people get confused or think impulse is some brand new concept, but as I've written here, the impulse on an object is simply the change in momentum of that object. That's all it is. So let me show you where impulse comes from, what its equation is, and how we can look at it graphically. So in algebra, we can write Newton's second law in this way. The force on an object is its change in momentum divided by the change in time, or in calculus terms, it would just be the rate of change of momentum with respect to time. Now, I want to just give you an intuitive sense for the calculus here. You don't need to actually know how to do any calculus at all. We're going to show both because I think it's helpful, and we're going to be able to use a calculus concept, the area under a graph, to look at impulse more closely. So I already stated above that impulse is just the change in momentum. So we're going to rearrange Newton's second law by multiplying both sides by delta t. So in just standard algebra form, which is the way you'd see it on your equation sheet, F times delta t, so the force times the amount of time that it's applied, is the change in momentum, which is the same as impulse. Sometimes you'll see either the lowercase or the uppercase letter J for impulse. To my knowledge, the AP doesn't really go that far, so we'll just leave it at this. In terms of calculus, same idea, just move the dt up there, multiply both sides, and you end up with the impulse is equal to force times a tiny change in time. That's equal to the tiny change in momentum. So impulse is something that is most often used in a graphical context, including in the context of rocket engines. So I'll show you that in just a moment. Before I do that, I want to show you a typical classroom scenario where you may get an impulse curve. So this is force plotted against time. It ends up being that if we take force and multiply it by time, which is going to be the area under a graph like this, you end up with units of momentum. So I want to show you that with an example that I took in the class. So here I've got a recording, a video of me letting a cart roll down a ramp and bump into this towel here. There's a little force sensor on the front, and what we're going to see on the right hand side in graphical analysis is a force plotted against time graph. So check that out. So you can see the force spikes over a short period of time during the collision, then it waits a minute, and then it does it again. I'll actually take a look. Here's the data. It rescaled, so it's easier to see. That was the first collision, the second, and the third. So what we're going to do now is I'm going to show you how you can get some useful information, in fact, the change in momentum of that object, by looking at these, what are called impulse curves you might see. So before we move into showing you a little bit more detail, I want to pause for a moment. This is actually a thing that people can do for fun because this is America and we sell model rockets to children. But I found this on a website for a company called Estes, which is pretty much the standard. They sell these little rocket engines. They're solid state. They're basically filled with a type of gunpowder that have a controlled release. And what's interesting is different types of engines will have different types of what you might call impulse or thrust curves. So, for example, your typical B6 engine is going to have a maximum thrust of 12 newtons, while the C6 is going to be a little bit bigger, and the D12 engine, I guess, is a really big one. It gets all the way up to 30 newtons worth of force. Now, what you'll notice, especially the difference between the B and the C class engines, is the sort of shape of the initial curve here. This one seems to last about a full second longer than the B6. Now what that ends up doing, even though they have a similar spike in force, is that the total change in momentum, which is the area under the graph, I'll show you that in just a moment, is going to be much bigger. So you're going to get a much bigger bang for your buck for something like a C6 engine, and something like a D12 engine has a very similar length of thrust, but a much bigger jump at the beginning, so it's likely that this one's actually going to give you the most bang for your buck. Now these, of course, vary in price and all kinds of things like that, but you too can have fun like this, father-daughter combo. Good stuff. So if you were actually going to hand calculate the impulse for a graph like this, using kind of the algebra methods you might see in AP, they're going to have to give you something like a triangle so that you can actually do the geometry and figure out the area under the curve. So here you've got your max force. It's going to be somewhere up here, and the force gets bigger and smaller, and the area underneath is going to be your impulse. So the impulse is going to be the area under the curve, because it's just F times t, which we've already defined as impulse. Now, if you're going to see something curvy like this, which is kind of what we saw here, this area, there's no real way you can do that by hand. So you're going to have to use, you're either going to have to be told what the impulse is. Here's our area under the graph. Or you'll have some other means of finding it out. So let me show you that in graphical analysis. You can see I've got my force versus time graph, and I can take the area under this graph. So what we'll do, let's see if I can get it exactly correct here. What we're going to do is we're going to see if we can actually calculate the change in momentum from just that spike. How much did the cart's momentum change? We can get it by taking the area under this graph. And the other thing we need to do is, by hand, we can calculate the momentum. Luckily, while I was letting that run, I also recorded the position, or rather the velocity versus time graph. So what we're going to do is we're going to hand calculate the change in momentum. We're going to compare it to the area under that graph and see if they come out the same, thus demonstrating what I was showing you here in the notes. So we want to calculate the change in momentum and see if it's equal to the area under the graph. To do that, we need to find some data. So we'll get the initial and final velocities. This looks like the final velocity after the collision. I'll write that down. Was negative, so V final was negative 0.299 meters per second. Let's find the initial velocity. So that looks like it would have been 0.840 meters per second. Take a moment, pause, see if you can calculate the change in momentum of the cart after this thing here, the first collision. So to do that, finding the change in momentum is as simple as taking the mass times the change in velocity. So I'll plug that information in and we'll get a number. Okay, so plugging everything in, being careful that I treat my negatives correctly, I get the change in momentum of our cart when it slammed into that towel on the end of the cart, or the track rather, was 0.327 kilograms meters per second. Remember, momentum doesn't have a fun unit. I did forget a negative sign here. Let's pop over to our experiment, and we want to make sure we're doing the same time. So 0.84 meters per second happened at 2.5 seconds, and then this time happened at 2.78 seconds. So let's make sure we're selecting the same time. Oops. Let's see if we can get it to do it. Well, let's just see if we can. I'll fix it in post here. So let's do, okay, view integral. Now it's a little bit off. Let's change our area. We want this to go out to 7.8 and this to go back to 5. Okay. So the impulse, the area under the graph, is 0.325 Newton seconds. So this area here, this area was 0.325 Newton seconds. If you work it out, you actually get, these are the same units, so that's confirmed. Now, why is this negative and this positive? That's because when I originally did this, I actually flipped the direction of this. So anyway, we get the same magnitude, we get the same result. The area under this graph is exactly equal to the impulse, or, within, a margin of error. There you go. Now that you know about this, if you watch movies about space or rocketry, you may hear them talk about impulse or something like delta V. What they're talking about is how much faster, how much more momentum is our rocket going to have after what we might call a burn or a rocket burn, where we're applying a force to our thing over a certain amount of time, and that will translate to a change in momentum of our rocket. There you have it, folks, all about impulse.